What is ET? No, not extraterrestrial. Evapotranspiration. That 7-syllable word that means water loss from a crop and the soil that is grown on. In this video, I'll use some acronyms known as ETO, ETC, ETA, KC, and I'll explain all those using real-world examples from 3 crops grown in California. In the early days of modern irrigated agriculture, meaning before sensors, there were and actually still are methods to extrapolate how much water a crop needs on a daily basis just using weather data. Irrigation scientists knew there was evaporative demand on a daily basis, but they needed to quantify that and use a standard. So looking back, weather stations were probably the first sensors used in irrigation scheduling. Multiple equations were derived over the years to estimate evaporative demand, particularly of a reference crop like grass. I'm trying to use a grass here in my neighborhood, which is not the best grass in the world, but it will do. The symbol ETO is internationally known for baseline evapotranspiration. Models such as Penman-Monteith or ASCE standards are some models that I can think of. Both those models use min-max temperature, relative humidity, solar radiation, and wind speed. Those all roll up to extrapolate and define ETO, or how much water a grass crop is taking in one day. So for crops, this estimation is known as ETC, C for crop, and versus the ETO, which is the grass. There are essentially 2 basic ways to derive ETC, but first you need a dimensionless constant known as a crop coefficient. A crop coefficient is just a fancy word for a constant. The 2 methods for deriving ETC are leaf area measurements at solar noon or lysimetry, which is really the gold standard. The leaf area method is inexpensive, yet not super accurate. But for years, prior to more advanced systems, scientists used this method to extrapolate the crop coefficient, or KC. As a brief example, if a crop shades 50% of a ground at solar noon, the theoretical crop coefficient, or KC, would be 0.5. Keep this in mind when I describe the second, more elaborate process known as lysimetry. Now let's explain lysimetry. Let's say you have 2 large boxes filled with soil, packed with the identical soil of the surrounding area and the same bulk density. And both those boxes are buried flush to the ground. The box on the left is planted with the grass or reference crop, while the box on the right is planted with your target crop. Both of these large boxes are placed on weighing platforms similar to truck scales. From midnight to midnight, data loggers record the weight loss based on each crop's evapotranspiration. The grass crop would be the ETO, and the target box would be the ETC. Let's say on a warm day, the grass box loses enough weight to be an equivalent of 0.3 inches or 8 millimeters of water, while the target box loses 0.15 inches or 4 millimeters of water. The ratio of the crop loss, or ETC, over the grass loss, or ETO, would be your crop coefficient. In our example, it would be 0.5. Capturing all this information scientifically for many crops, be it from the shade method or lysimetry, that's an elaborate process. I want to give a shout out to the many irrigation scientists over the years that spent their careers coming up with these numbers in order to predict crop water loss for just the noble goal of irrigating correctly and using water efficiently. Now let's apply some of these equations to some real-world examples in California. Let's take a look at almonds in the San Joaquin Valley, lettuce in the Salinas Valley, and carrots in the Imperial Valley. I've kept things really simple when I put this box together for each crop KCs. So I just focused on the early season, mid-season, and late season of each crop and put their KCs accordingly. Notice how the almonds and even the carrots KCs actually exceed 1. This means that at that stage, they use more water per unit area than a well-watered lawn would. This is due to canopy architecture and multiple layers of leaves. Now, let's take a look at the ETO from weather data from those regions, multiply that data by each crop's KCs to match the time of year and stage to produce a nice ETC chart for all 3 crops. Notice that the carrots in the Imperial Valley and the lettuce in the Salinas Valley peak for their ETCs. But for almonds in the San Joaquin Valley, the curvilinear shape is due to it being a permanent crop, using water a lot longer, and also experiencing more of the season than a vegetable crop. Finally, I mentioned ETA earlier. ETA is an example of a more direct measurement of evapotranspiration of a crop. I'll cover that later when we come to sensors. If you stuck with me so far, you've been a great student. Join me next time on California Soil and Water, where I'll cover another agronomic topic.